position. So
Okay, so now we have Joonas Turunen to tell us about the critical Ising model of infinite random triangulations of the disk.
All right, thank you for the organizers, and I'm going to talk about joint work with Lingsha Chen, who also work in my university in Helsinki, and this is based on this archive preprint. And my topic is going to be critical Ising model on triangulations of a disk. And well, let's start from the basics. So we study rooted planar maps which have only triangular faces in the interior, and then there's a polygon boundary without pinch points. So it's basically we have a simple polygon on a sphere, and then inside the polygon we have a triangulation. And then I denote by ft, like t is now the triangulation, and ft is number of faces, internal faces. And then we add to each internal face a spin, either plus or minus. And then I denote by sigma spin configuration on that triangulation. And then edge. An edge is called monochromatic if it separates two faces with the same spin. And I denote by mt sigma the number of monochromatic edges. So naturally here we need the sigma also to count the edges, okay? And then we need still a boundary condition to have a well-defined Ising model. So I consider here those so-called Dobrosin boundary conditions, which means that the spins outside the boundary are fixed in two sequences. Like first we have p plus spins and then q minus spins, where p and q are now some fixed numbers, and well, we put the spins on counterclockwise around the root. All right, so maybe the next picture explains a bit more. So here we have just a triangulation of a p-gon and without any spin. And here this means that, well, we don't consider that kind of pinch points, so our boundary curve needs to be simple. And then we root the triangulation in some corner here. And in this example, number of faces is 18. You can easily count it if you want. And here, what's notable is that we can also consider like loops like here and multiple edges like here. So those are allowed in our model. And then in the second picture, we have a Ising spin configuration on this left side triangulation. So here now this boundary is divided by two segments. There's like p plus spins and q minus spins, and in this setting, well, p is 3 and q is minus, and q is 4. And then here inside we have a spin configuration which we encode by two colors here. The color code is like that purple color represent spin plus. And then in this setting the number of monochromatic edges is 17, and in this picture those monochromatic edges are represented by those dashed lines. Okay? And then we can define a partition function of this model. So we fix the numbers p and q, which are now the boundary length, and then we sum over all the Ising triangulations of this p plus q gon with this Dobrosin boundary condition of type p plus q minus. And here what we should note is that here this nu is now the coupling constant for the Ising model. So it's basically exponential of the inverse temperature. And it's to the power of the monochromatic edges. And then this t is the coupling constant for a number of phases. So in the setting, if we set nu to be 1, then this is just a like pure gravity triangulations of a p-gon. Okay? And yeah. So next, in order to, well, we want to basically estimate those or find the asymptotics of this g, p, q, and p and q are large. So then we encode them by generating function z, which has now two variables, since we have here those two boundary segments p and q. And then first of all, this is a formal power series, so it's totally well defined as a combinatorial object, and we can write a recursive equation for it, the so-called touch equation, and then we can also solve that touch equation so that we find an explicit rational parameterization for this generating function. And once we find this, we can study the singularity structure of this Z. And then we have a powerful machinery of analytic combinatorics, which allows us to extract those coefficients once we know the location of the dominant singularities and understand if that there are no other singularities disturbing. Okay, and then there's a previous work of Bernardi and Bousquet-Mellot where they basically identify a critical point of this model in the case when Q is 0 and P is, let's say, smaller than 3. And we can translate this critical point to our model. And basically, in the sequel, we work on this critical point since there are basically two reasons. First reason is that we assume the most interesting phenomena happen here. And the second one is it's easier for computations. Okay. So this is our first theorem. It says that this generating function Z is an algebraic function and it has an explicit rational parameterization. So we have here two variables h and k which parameterize this to the same curve with u and v. And this is now the explicit expression, and this d is quite nice. It's degree 4 in both of those variables, and this n is not that nice. It's around degree 10. But still there, we can write them down and we can do calculations with them. And then from this we can extract the asymptotics of ZPQ by using analytic combinatorics. So first, if we set Q, which is now the minus boundary length, to go infinity, then this behavior is like this. So first of all, note here the exponent minus 7 over 3, which is different to uniform triangulations of the disk. So in the uniform case, I mean the pure gravity case, the exponent will be 5 over 2, but here it's 7 over 3, so there will be a notable difference in the critical behavior. And then this UC is now the dominant singularity of this generating function, more or less. And then this AP coefficient depends on the plus boundary length, and if we also study the large plus boundary length, we will find this behavior for the coefficient. All right. So now, once we know the behavior of this ZPQ and PQ large, we can approach this Boltzmann distribution, which we can define for any P and Q finite. And this is just the, straightforward generalization of the Boltzmann distribution in the UIPT case. And this also corresponds to the canonical distribution of Ising model in our setting. Okay. And here is an example of such a configuration. So we have the same triangulation as our previous example. And here's a number of interfaces was 18 and monochromatic edges number was 17. So then we just plug here them in and get this kind of number. And of course this Z3, 4 might be hard to compute, but when P and Q are large, we can estimate it by the asymptotics. All right, any questions so far? All right, so then our second main theorem is that actually those Boltzmann distributions have local limits when P and Q go to infinity. So first we set Q, the minus boundary length, to go to infinity. So we get a distribution which depends only on the plus boundary with respect to local distance. And what does it really mean? So if we now have some triangulation with the finite boundary of length Q minus spins and P plus spins, then we study some, here's now the root vortex. So we study this triangulation inside a combinatorial ball of radius r. And what is the distribution inside here in the ball? And if this converts inside any such ball, then we say that it converts locally. So in this case, when Q goes to infinity first, we will get this kind of model. So we have first some infinite number of minus boundary, and then we have some finite plus boundary of length P, and then again infinite minus boundary. And here is now the root vertex, so we study some ball of radius r around here. And then the second convergence here, we set the p go to infinity, so we get basically, we get then just a half plane with two infinite boundary segments. So here is infinite number of minus and here infinite number of plus. Okay? Alright, so now I show the idea how to basically find the touch equation. So here first we start from the boundary of length p and q, and then we choose here the root edge next to the root vertex row. And then first we want to explore the triangulation which is incident to this root edge e. So here's basically listed all the cases which might happen. So it might have either spin plus or minus, and then the third vertex might be either in the interior of the unexplored triangulation, which I call U here, or it can be on the boundary. And then if it's on the boundary, well, it has some number of edges k along the boundary to each of the direction. So then I encode these events by those numbers c plus and rk and lk with the corresponding spins. And well, this is a graphical representation of how we derive the touch equation. So here we just need to subtract one event which belongs both here and here. Okay, so actually this touch equation also defines probably the distribution on the set of symbols like this, and it's basically the first peeling step we want to do. So we want to define a peeling process which basically explores the Ising interface. So this is the most natural way to do it. So since our boundary is always Dobrusian, then all of these operations preserve the Dobrusian boundary. Once we choose here always one triangulation to peel. But anyway, we find the Dobrusian stable peeling process by this way. And so if this is viewed in the first peeling step, then we can also first of all study limits of those peeling steps, and we find also probability distributions in the q equals infinity and p and q equal infinity setting. So this is the basically building block of our local limits. So then we can iterate this peeling process, and then we obtain some explored map and corresponding unexplored map. And to each unexplored map we can assume a new perimeter, which is now, some random number which depends on the n, which is now the number of peeling steps so far. And this is called perimeter process. And it will be a two-dimensional Markov chain. And if p and q are finite, then we can define also a perimeter variation by just, well, we subtract from a perimeter at time n the initial perimeter. And this can be also defined in the infinite setting, since it only depends on the first n peeling steps. And here is a picture about this. So here is now we have conducted n peeling steps. Here's the root, and we started exploring from the boundary, and we have explored so far this kind of triangulation after n steps. And then here's a new root, and the boundary is again Dobrusian, and here qn is the number of minus edges here, and pn is the number of plus edges here. And then here is now what is in the unexplored parts. And then we want to explore this triangulation here. So as you see, it will be of this type, and then we explore it, and actually it splits the boundary to two parts. So then we need to choose one part we want to continue the peeling, so we choose this one, etc. So we can iterate this, and this is called now the peeling process. Okay. And well, it turns out that the perimeter variation at time n under this p infinity measure, it's a random walk on Z2, and moreover those marginals have this kind of drift, which is positive, and this is basically why our interface will drift to infinity, and it will only touch the boundary of the half plane a finite number of times. And then we can also show, because of the asymptotic formula for the partition function, we can show that actually those two like first boundary variations, they have a polynomial heavy tail of index 4/3, so they belong to the domain of attraction of a 4/3 stable law. And here is actually we can prove something more. So from this result, basically it follows that those marginals of this process converge towards a stable law, but actually we can show that they converge jointly, even though they are not independent. And yeah, this is the first scaling limit result we have. And then next one, we have a second scaling limit result that if we now still let the plus boundary to be finite, then this perimeter process of the plus boundary have a scaling limit when p goes to infinity. And what happens basically, the perimeter process looks like this. So we start from the value p, and then we have some linear barrier in which the process stays until at some time it jumps to the neighborhood of 0. And in the scaling limit, this part will it will converge to a linear function, and here will be some random time, let's say t, which will converge towards this random time here. And moreover, this random time has, this random time has this kind of power law. And after some discussions around here, we conjecture that this law could be obtained also by gluing some quantum disks and studying the law of the interface curve in that gluing. And then we conjecture that actually this random time here can be replaced by the length of the main interface, which is basically now the interface which converges to infinity, so that we could obtain some sort of scalar limit of interface. All right. And then I will briefly mention the ideas of the proof. So first of all, t0, which is now the time p in the perimeter process, hits 0. So if we have here, if this process goes to 0, then we can put here t0. Okay. So it turns out that for each p, it will be almost surely finite. And then, it basically tells us that we can explore around any finite cluster in a finite time, and that's pretty much the idea. We can show the first local convergence. And then we can also show that this, basically what I explained here, that this perimeter process Pn jumps to close to 0 with really high probability if P is large. And it's essentially because it's close to heavy-tailed random walks which have the one jump principle. And then we have the positive drift of the perimeter variations. So it tells that, okay, under this P infinity, the peeling process will drift to infinity, so we have no hope to explore the whole triangulation. But anyway, we can explore something which we call a ribbon. And how does it look like? It's like this kind of infinite strip where actually the peeling process stays in some finite interval. Well, it will never touch the boundary of the half plane after some time. And then once we do this and we have shown the local convergence for any fixed p, then we chose a p to be 0. We find those triangulations with monogrammatic boundary. So these are also triangulations of the half plane, and then we glue them together with the ribbon along those plus and minus boundaries, so that we get a triangulation of the half plane with two colors, the bruising boundary. and then we can show that actually the law of this will be the same as the law of the local limit, which basically proves our local limit result. Okay, and then once we still have like 1 minute or half a minute, I will explain a bit about the interfacing clusters. So if P is finite, still in Q is infinity. So we have this kind of structure. There's some giant plus cluster around this boundary, and then the other plus clusters are rather small. And then once we take the local limit, we will have some, like this kind of picture where we have like two infinite regimes, like minus and plus, and then inside this regime all the plus clusters are finite, and here the vice versa after inversion of spins. All right, and then there are some works in progress and future directions. So for example, study the off-critical regime, like near the critical point, and what kind of change in the geometry happens around the critical point. That's under progress. And then also we can study the universality by studying related models, and also study other lattices, perhaps using, for example, different methods. For example, matrix integrals. That's also one option, and of course more general boundary conditions and so on. And in the end, well, we're really interested in scaling limits of this model, so maybe a far-time goal would be characterize a scaling limit model as a Liouville quantum gravity service. So, all right, so thank you.
So, in order to get your left-right boundary length process to converge to a stable process, you have to subtract off n times the mean.
Ah, okay.
Right. So I'm wondering if you have a geometric interpretation of
this one.
Yeah, x sub nt minus mu nt.
Ah, okay. So it's basically, what is this x1? Well, we have the peeling process, and we have it on the half plane. So basically, we have, for example, here, if we have here even plus like this, then the x1, y1 will be 2 and minus 1, or like this. So it's basically just tells how the perimeter changes after one step, and then actually this perimeter fluctuation will be a random walk. So basically now this is just the fluctuation of that random walk around the mean and its scaling limit, but I don't really have any idea now how to use it, but probably later on, if we want to understand the scaling limits of the interface better. For example, if we could also understand scaling limits of the volume of some balls, then we could try to repeat something which is already done in the UIPT case. Okay, any other question?
Just a remark. You mentioned Bernardi and Busquemelu,
yeah?
But actually, you know that was in physics, the famous paper by Kazakov.
Yes, yes. So basically,
looking at 4 coordinate lattice, but using random matrices.
Yeah, that's true. That's true. Yeah.
It played an important role because that was really the first paper.
Yeah.
Where they solved a statistical mechanics model, and that showed, and thanks to KPZ, thanks to this, they believe that Liouville quantum gravity would be the scaling limit of the random surfaces model.
Yeah.
So,
yeah.
Do you know that some info on the ratio between Cx and Cy say that it's 2, or do you have information about the
ratio of Cx and Cy? Well, basically, the only thing we know is, well, why we have this asymmetry is that we choose our peeling process always peel from the minus boundary. So we could also choose it to peel plus boundary, and then we would have that actually the Cy will be bigger than Cx. But otherwise, I don't really know.
It's not any integer or nice numbers.
so we can discuss?
Any more questions? Okay, we have a 3 minutes break until the next lecture. Let's thanks.